Good morning, everyone. Yes, good morning. Shall we begin the session? Today is a continuation of the last topic, that is the fetch cycle. In the last class, we have discussed only the theory of the fetch cycle. Now we will discuss the flow chart of the fetch cycle. What is the fetch cycle? How the fetching will be done, or how we fetch the data that is available within the fetch cycle. So shall we begin? All right. So fetch cycle is used to decode or to enable the things, whatever the things that is available to decode the material, to decode the we can say the instruction cycle. So fetches the instruction from the memory, then execute cycle. This is for the decoding the instructions, fetch required instructions, and perform the operation. Instruction cycle comprises of a sequence of the micro operations. Micro operations includes whatever the operation, each of which involves a transfer of the data to and from the registers. Whatever the data, whatever the registers, that is the micro operations, each of which involves transfer to and from register. Whatever the data, whatever the register that is available, this can be used with registration of the data, with the usage of the data that is available within the scenario. So each of which involves a transfer of the data, or the registration or the transfer of the data from one register to another register. And in addition to executing the instruction, the CPU supervises other system component, usually via a special control line. What is that special control line? That is the CPU that supervises each and every component by which it is usually done. And it controls input-output operation. Whatever the input-output operation that I'm asking for, this readouts the input output operation that is used. So this is either directly done or either indirectly done. And since input output operation is done, it's a relatively infrequent event. The input output devices are usually ignored until they eventually, or until they actively request the service from the CPU via an interrupt. So whether the interrupt criteria that is available for the CPU, that means interrupt is done or interrupt is carried out. Interrupt is, we can say, the processed by the criteria that is known as the instruction cycle. Now this is the interrupt instructions one, A1, A2 till A5, then B1, B2 till Bn, and the interrupt is activated by an electronic signal. So whatever the interrupt, whatever the data that is activated by an electronic signal, and the branch to new set of the instructions. Now this is one of the instruction cycle. This is the start, then the instruction awaiting for the execution. So whatever the instruction, whatever the data, whatever the command we are given, that is awaiting for the instructions. Then if it is yes, then fetch the new instruction. If it is no, then execute. Yes, if it is no, then again go back to the start. If it is yes, then fetch the new, next instruction, that is done by the fetch cycle. Then execute the next instruction, that is by the execute cycle. Then interrupt requiring services, that means whatever the interrupt that requires a service, if there is a yes, then also transfer to the interrupt handling program and the program transfer. This is the interrupt that acquiring the data, that in acquiring or interrupt requiring the services, whatever the service that is required, whatever the service that is used, over to the transfer the control to interrupt the handling program. Now this is one of the example of the program that is available. So this is the next program that is used for this. So there is the main program, then main program is load B, then subroutine is OP1, interrupt handler this one. Now there is the interrupt handler that is in the bits 1111 8 times say 1, then B, this is 01001100, then C, then 7 times 0, and then 1. So this is the main program, load B, add C, store A, then subroutine A, that is operation 1, operation 1, operation 1, interrupt handler is again operation 1, operation 1, operation 1. Then the CPU is AR, DR, AR is PC, then IR control unit, DR, AC, arithmetic and the logical circuits, then ALU, arithmetic and the logical unit. Now there is a register transfer language. So whatever the language we are using, whatever the transfer procedure we are using, that is a register transfer language that is provided with the data, that is used with the data. So there's a storage location in the CPU and the memory as referred as acronym. So whatever the acronym, whatever the anonyms, that means whatever the similar word that is we are acquiring, that is a storage location in the CPU and the memory. Then there is accumulator, that is the main operand register of the ALU. Then DR, that is a data register that acts as a buffer between the CPU and the main memory, and that is used as input operand register. So whatever the operand register that is used with the accumulator to facilitate the operation of the form AC, that is F, AC and the DR. So whatever the AC, whatever the DR, that is accumulator, whatever the data register that is used to accumulate or facilitate the operation of the data. That is F, AC and the DR. Then the register transfer language, that is again the PC program counter, restores the address of the next instruction to be executed. Whatever the instruction that is executed over here, that next instruction is executed over the data over the period of the time. Then IR, instruction register, so this holds the opcode of the current instruction. Whatever the current instruction that we are handling, so this is the opcode of the current instruction, that is IR. Then AR, that is address register, so this holds a memory address of an operand. So whatever the memory address, for example, if I'm declaring a variable, this is num equals to a plus b, that means num is also a variable, a and b are also a variable, but these variables store in some address location. That address location, for example 1011, this address location is stored in the address register, not the variable but the address register. This is A arrow B. This transfer the content of the storage location of B to A. Whatever the content, whatever the variable that is available on the right hand side, that content will be going into the left hand side. Then A arrow MADR. This transfer the content of the memory at the location ADR to the location A. Now next is again the fetch cycle. This is the start. Then if the CPU is activated, yes, then the PC is going into the AR. Memory of the AR is going into the DR, and the DR is again going into the IR. This increments the PC and the decodes the instruction. Again, it is used for the adding the instruction. If there is a no, then store the location. Then start, add instruction no, store instruction yes, then AR arrow DR, that is address, then DR arrow memory of the AR, then AC yes. Output of the AC and the DR, that is accumulator, and the data register is added into the accumulator, that is AC. This is known as the fetch cycle, execute cycle. Then evaluate an assignment. How to evaluate an assignment? This is A equals to B plus C. So first of all load the B. So that means first of all load the B means first of all use the variable B, then add the variable C, then output of B and C is adding into the store, or output is storage into the A. This is load B, then PC, AR, memory of AR is DR, then DR opcode is IR, then increment PC, decode the instruction in the IR, then AR, yes, address is going into the AR, then yes, then the memory of the AR is going into the DR, then DR is going into the AC. So till now, any doubts anyone? Next is extensions to the basic organization and the binary number representation. So we have done with the binary representations, or the binary number representation. Now there is the extension of the binary number representation, or we can say next part of the binary representation of the basic organization. So first of all, there is additional addressable registers for storing the operands and the addresses. If these are the multipurpose, yes, if these are the multipurpose extensions, so we have it is known as a general organization. So special address registers are also provided for the purpose of memory address construction, that is known as a index register. And the capabilities of the ALU circuits can be extended to include the multiplication and the division. Now, the ALU circuits are available for the addition, subtraction, division, and the multiplication. And the ALU can also process the full floating point number. It's not mandatory that it only deals with the instruction, it only deals with the, we can say only the product or the real number, but it also deals with the floating numbers. And the additional registers can be provided for storing the instructions, whatever the register, whatever the data that is acquired. So these registers can be provided for storing the instruction, for storing the data. So these are the extensions to the binary system, so the binary arithmetics. Then special circuitry to facilitate the temporary transfer to subordinates or the subroutines or interrupt handling programs and recovery of the original status of the interrupted program on returning from the interrupt handler. Whatever the interrupt handler situation, whatever the circuitry that is used to facilitate the temporary transfer to the subroutines. Example, the use of a push down stack implies that we need only a special purpose stack pointer register. Then there's a parallel processing. So parallel processing means simultaneous processing of two or more distinct instruction or the data streams. That means more and more, or the simultaneous means at the same time there is a processing of two or more distinct instructions or the data streams. The information representation, that is the types of the data that includes the text, that includes the numbers, that includes the integer and the reals. Then text, that is in the SCI format. This is the American Standard Code or the Committee on Information Interchange. Then there is a unique 8-bit binary code for each character. This is from the capital A to Z. This next is small a to Z, 1 to 9 underscores. And the special unprintable character such as the enter key, that is CR for the carriage return. Then binary number representation of the integers. So if we say 1 bit to signify the positive or negative, then an n bit binary word can represent integer in the range. For example, when you talk about the 16-bit binary number, that can represent the integer in the range. Then there is a 16-bit binary number. This is 0000, 0001, 1001, 1111. So this is a 16-bit binary representation. That means 16 number is right. 16-bit binary number means, yes, there are total 16-bit binary digit 4444, 448, then 816. This is start with a 0 from the left hand side, right hand side, 0, 1, 2, 3, then 4, 5, 6, 7, then 9, 8, 9, 10, 11, then 12, 13, 14, 15. So this is 16-bit binary number is represented from the 0 to the 15. Now, for example, if I want to calculate this one, this is 2 power 0 into 1, then 2 power 1 into 1, then 2 power 2 into 2, again 1, sorry, then 2 power 3 into 1, 2 power 4 into 1, then 2 power 7 into 1. Why? Because there is no value of the 0, so we can't use 2 power 5, 2 power 6, then 2 power 7 into 1, then 2 power 8 into 1, and else everything is 0. So there is no requirement of the 0. So everything is 0. That means 2 power 8, 256 into 1 is 256, then 128 into 1, 128, then 16 into 1, 16, then 8 into 1, 8, then 4 into 1, 4, then 2 into 1, 2, then 2 power 0. Any digit have a power 0 is 1. So 1 into 1 is 1. This is when I add everything, this is 415. Now, if we let the most significant digit or the bit signifies either positive or the negative number, 1 for the negative, 0 for the positive. Then plus 9 is 000000000000001. Then minus 9 is 1 is the most significant bit, then 1001 at the end. Then plus 9 plus minus 9, this is 1000000000. Then 00010010. Which is not 0, that is a problem. Now the number, so we need a different representative for the negative numbers known as a 2's complement. Take the 1 complement of the positive numbers. Then this is the one complement of the positive number, that becomes one's complement means adding the 1 over here. Now there's a number, note that the addition of the one's complement and the original number is not 0. This is 0 plus 1 0 0 0. This becomes 1 1 1 1 1 1 1 1 1 1 1. But if I use 1 plus 1, that means 0 is a remainder and 1 is carry. That is 1 plus 1. And to get the 2's complement, we add the 1 over here. So this is 0 plus 1 is 0. Over here, 0 plus 1 is 0. Then again there's a 1, then 1, then 0, then 1, 1, 1, 1, 1. Everything is 1 over there. Now, do the addition of this. And as I said, 1 plus 1 is 0 and the remainder is 1. Now again it is 1 plus 0 is 1. 1 plus 1 is 0, then remainder carry is 1. Then 1 plus 0 is 1. 1 plus 1 is 0. Again it is 1. 1 plus 1 is 0. 1. Again it is 1 plus 1 is 0. 1. 1. And it is going on, 0, 0, 0, 0 at the end. That's the 1 plus 1 is 0. So everything is 0 over here. This is plus 1 minus 1. And plus 1 minus is always 0. Now this is the shorthand notation for these ones and the 0. That is for the hexadecimal notations. And each group of the 4 digit or the 4 bits represents a number in the range from the 0 to the 15. So that number is given in the range from 0 to 15. Because as I said, this is a 16-bit integer. That range is from the 0 to the 15. Not from 0 to 8, nothing. But 0 to 50. So these are the numbers. 0 0 0 0 is 0, then 0 0 0 is 1, then 2, then 3, then 4, then 5, then 6, then 7, 8, 9, A, B, C, D, E, F. Then these are the numbers that is representing. There are 3 zeros and 9, then 3F and the 7. Now hexadecimal is used as a notation for any sequence of the bits. That is, a sky character requires just 2 hexadecimal digits. The next is the digital design. There's the design hierarchy. Many digital systems can be divided into 3 design levels that forms a well-defined hierarchy. One is the architecture level, one is a logical level, one is a physical level. And in the architecture level, there is a high level concerned with overall system management. Then logical level, there is an intermediate level, that means it is the mid-level that provides with the technical details of the system. Then physical level, that is the low level concerned with details needed to manufacture or assemble a system. Then we have already studied the architecture level. Now we will address the logical level. That the logical level, there are 2 classes. One is a combinational, one is a sequential. And the analog signal can have any value within the certain operating limits. For example, when you talk about the amplifier, the output can have any value between 0 volt and the 10 volt. And the digital signal can have only a fixed number of the value within a certain tolerances. This is the analog signal, and the amplitude is sampled with a discrete time interval, discrete time data, that is sample version of the analog signals. And this is a simplified or the sampled version of the analog signals. Then the amplitude may be restricted to take on the discrete values only, in which case it is said to be the quantized. That means it is used as a quantized or the analog as the digital data. Then there's a calculation with the number that is usually done in the base 10 arithmetic. Then easier to affect the machine computation in the base 2 or the binary notation. Whatever the effect computation, whatever the data that is available, that is used in the machine computation, that is used in the base 2 or the binary notation. And we can also use base 2 or the binary notation to represent the logical values or the true value, that is either true or false. Then the manipulation of these logical values is subject to the laws of the logic, that is known as a Boolean algebra. So one is either two notations, either true or the false. One is a Boolean algebra that represents what are the various rules, what are the various laws of the digital circuit. Then next is a logical variable, that is x can have only one of the possible values of the states. one is true, one is a false. And in the binary notation, we can see true is 1 and the false is 0. That is the positive logic or the high true logic. And electrically, 1 is represented by a more positive voltage than 0, and 0 is represented by the 0 volts. There's a true and the false. Then logic gates are switching circuit that perform certain simple operations on a binary signals, and these operations are chosen to facilitate the implementation of the useful functions. And the AND logic operation, consider the following condition, consider the following circuit. There is a bulb that represents in the AND truth table, this is A equals to A and B. This is 0, 0, 0, 0, 1, 0, 1, 0, 0. This is the AND gate. This is, we can say, the A into B. A and B are variables, and note the use of the dot to denote the AND. Then this is one of the example. Determine the output waveform when applied with the input waveform.